So today's topic is all about load paths. So what are load paths and why are they important? If we boil it right down, a load path is essentially the way that a load travels from where it is applied to its final destination, which is usually the ground. And they enable us to understand how a structure will work and behave so that we can make accurate estimates on how they will act and how they will behave if we carry out some structural amendments. Incorrect assumptions on load paths or incorrect understandings on them can cause structural instability. It can cause cracking, failure, unexpected loadings, which can lead to catastrophic effects, really. And that's why it's really important that we understand how a structure works and behaves and its load path so we can avoid some unsafe conditions on site. I've put in a code on here, which is the British standard for partial and full demolition. It's BS 6187. Load paths in structures that are being demolished change very regularly, and therefore it's a residual risk on complex structures. Unplanned collapses can be avoided if we fully understand how a structure works and therefore how it will behave when we start actually removing certain structural elements. But the word load path crops up a number of times in this document, and that's quite understandable, really, because this construction information on a structure being demolished is not always available, so we've got to make our best guess or an educated assessment. This is very different to a new structure being built, because we've got all of the details, so we know exactly what's going on, and we can make a very, very accurate understanding, or very accurate estimate and understanding of what's going on there. So the chances of misunderstanding is much greater for a structure during demolition, be it partial or full. And the key section of where load paths is mentioned in BS 6187 is in section 14, where it states that any demolition should be based on complete understanding of the nature of the structure, understanding of the independence of all the structural elements and all the interrelationships with adjacent structures and surrounding environment. And then it goes on to say that the understanding of load paths is essential to enable the strategic use of the inherent structural relationships, which, put very simply, it's quite a fancy pants way of saying that we're basically relying on the structure standing up during the demolition works. The same applies to new structures being constructed, as it's essentially the reverse of the demolition, or demolition is the reverse of construction. But whichever way you look at it, reverse or forward or backwards or swinging from a light bulb, the stability of a structure relies on a good understanding of how the structure works, which load paths is a very large part of that. So what happens if things go wrong? What happens if we think a structure behaves in one way and it actually behaves very differently? Well, potentially some pretty catastrophic effects. Misunderstanding how important a structural element is to a building supports or could lead to full or uncontrolled collapse of a significant part of the building, if not the whole building, through the kind of domino effect of collapse or disproportionate collapse. And it comes down to GIGO, which is garbage in and garbage out. Without full and detailed understanding of how a structure behaves, we can't get to that right output at the end. And we need to feed ourselves with the correct information, which may be structural drawings or site investigation, to give us that proper understanding that we require to determine the correct and best solution going forward. Okay, so now we know that a load path is the way that a load travels from where the load is applied to its final destination. We're going to now briefly discuss what these loads can be. These can be broadly split up into two categories. So we have the vertical and horizontal or lateral loadings. So vertical loads, we're talking about things going down generally or up. Gravity is key. So gravity and its effect on the self-weight of the building, acting down due to gravity. Imposed loadings, so these are live loadings such as pedestrian loadings or vehicle loadings or environmental loadings such as snow, all pushing down on a particular element of a structure and that load feeding down. And then we've also got the second category, which is lateral loading. So this is gravity loading such as the self-weight of soil, for example, kind of loading down and moving out and pushing up against a retaining structure, or if the structure is leaning, it could be having that eccentric effect on the structure. And then the lateral loadings from imposed loadings such as wind or waves, things like that. And then the third one I've added in there is also important to consider the combined load effects and the load cases that you get from these forces when they act together and they follow that same load path. That's very important to consider. So here we've got a conventional load path of quite a basic structure. This could be a reinforced concrete slab on a concrete or steel frame comprising of beams and columns that are themselves founded on some pad foundations that are on the earth. As the illustration shows, the load of the slab, if we've got a gravity load in the center or the self-weight of the structure, or indeed a imposed load, then that load from the slab follows the structure from the slab, then distributed to the beam, and then to the columns, and then finally down to the foundation, where an equal and opposite reaction force resists that total loading and kind of resists that, so it prevents the structure from sinking down into the ground. We've got another relatively basic structure here, which is a more domestic type arrangement. And here again, we can see that loading from the roof and the other structures coming down and ultimately be resisted by the foundations at the bottom. So it's starting at the top and all kind of filtering down through beams and walls until we get to the foundations at the bottom. A real life example of a slab and steel frame. We've got the load moving from the slab across to the secondary beams, and depending if it's a one-way or a two-way spanning slab, it may well behave differently and go to different beams. And then from the secondary beams, we're moving across, and that load is being chased down to the primary beams, okay, and then down to columns, which eventually go down to the foundations of the structure. It's the same for any kind of structure, so it includes temporary works and temporary propping, and we've got that same kind of pattern here, okay? So we've got the temporary load coming down through the slab and onto our propping arrangement. Then the beam is distributing that load down to the columns, which again is going to be resisted at foundation level. These are pretty conventional load paths, things that you can see directly, you can understand. It's following from top to bottom and starting at the top and ending up at the foundation level. Pretty conventional. I've got a couple of examples here of where load paths are really important for when removing structures. So actions as simple as lifting out an existing bridge, for example, with a crane must be given some thought. And at first glance, we might say that since the support points are being brought close together, where we're picking up this bridge and removing it and sitting it down onto a low loader to be taken away, if we're bringing those supports in closer together, then we're going to have lower stresses, or we're going to have a lower bending moment, right? Yeah, of course, that's a valid point and correct, but we need to understand these new support conditions and what effects they're going to have. So as we pick up the bridge, the ends are going to want to drop down, which means that we're going to have hogging moments over those lifting points, i.e. that bridge is going to try and break its back over those support points where we are supporting with the crane. In the actual case of where it is supported previously, it's going to be straining on its belly. So we're totally reversing the loadings from being at the bottom, the tension face being at the bottom, to the tension face being at the top. And that stress distribution in the cross section is going to be totally reversed, putting the top half in tension and the bottom in compression, which is really important to understand of what materials are being used in that structure, as well as if it's seen that force before, because we don't know what the kind of connection details are, for example. So this is especially important when we've got materials such as cast iron, which have very different tension and compression capacities as are being considered as, and the restraint conditions on the flanges may well be different as well between the top and the bottom. So on the right hand side here, on this photo on the top right, we've got a post-tension bridge as well, which is especially designed for its design support conditions, and any alterations to that can also be disastrous, really, if the support conditions are changed and not given due consideration. Not something you want to happen when you're hanging it off the end of a crane. So another point I briefly mentioned there was the conditions of the structure. So if we are keeping the forces within the structure as what we're happy with from a theoretical standpoint, then we need to consider the condition of the structure. If it's corroded or if it's on dilapidated structures, then we need to consider those reductions in cross-sectional area or damaged connections, which could result in a significantly reduced resistance to those members. And then once all of those factors are mentioned, that we've mentioned, are considered, we can then provide a successful design and a suitable output, in which we did in both these cases. But remember that just because a structure can do something in theory, we need to make sure that it will also behave like that in practice. So a low risk option would be to ensure that the structure doesn't see any stresses worse than it during its design life, to ensure that we're not pushing that structure past what it can handle. So how do we know what these load paths are? We know about them, we know that they're important to understand, but when we're looking at a structure right in front of our eyes, how do we know what the load path is? We need to have a deep understanding of that structure, which is developed from a desktop study and also intrusive site investigation. And it's important that a competent person reviews this information and is confident in their conclusions. Sometimes the simplest operations of creating a door opening, as shown here in this little photo, can be quite tricky. There could be a lot of stuff going on there, so it needs to be considered. So what does that mean in our real life projects? So it means having a thorough understanding of the structures, how they work, typical structural arrangements, experience of similar structures. That helps a great deal. It means reviewing archive drawings if they're available. They're not always available. And also remembering that just because it is an archive drawing, it doesn't mean that they're as built. I've seen many drawings which even stamped as built, which have not even similar to the structure that's there. So we need to be careful there. Intrusive site investigation, such as breakouts in the structure to expose key structural elements, confirming any assumptions or finding new information, especially if there is an assumption which is critical or has lack of redundancy, then we need to really make sure we confirm those to make sure what is on site is what we expect. And it's a good idea to have a walkover survey post soft strip stage, so that you can have a really good look at the bare structure and understand what's going on. That's going to give you a really good understanding of how the structure works. So here are a few items that need to be considered when it comes to load paths. How is the structure currently standing up? Chase the load from all the way at the top to the bottom where the foundations are, and kind of justify to yourself how the structure is able to remain standing as it is. And then how does that load path change if there's any settlement? If a support drops or is removed, where does that load go? Is there any redundancy, or is that going to be an issue? And sometimes it's not when there is a structure being demolished anyway. The load transfer from temporary to permanent structures is really important and requires some thought. The overall stability of the structure as well, taking into account any openings that have been created. Are we creating a structure that looks like a block of Swiss cheese, putting lots of holes in it, doorways, floor openings? And if so, we need to have a lot of confidence that the load passes, there will be very little redundancy in those supports in the structure. Is there a stage during construction that is not covered by the permanent works end condition? And by this end condition, I mean that if you are to have a structure that is being conventionally constructed from bottom up, with stability mechanisms being constructed with the structure, then the worst case stability case will be when the whole thing is completed. So therefore, by default, all the previous stages are therefore acceptable. However, if the structure is being constructed in a slightly different manner, then this needs to be considered by a competent person to ensure that the structure remains stable during construction, i.e. we've got those stability mechanisms in place. And then finally ask yourself, is this buildable? And has the load path been considered for the whole sequence, i.e. step by step? Visualize the process in your head and imagine it. And you may spot potential footfalls which can be eliminated in the planning stage and not left to anyone's site. There's one last final point that I'd like to make before I'm going to pass on to James, who's going to take us through some more unconventional load paths. But I'd just like to cover load history phenomena. So this is certainly something that can catch you out if you're caught unawares and you don't really know about it. I'm going to explain through a real life example on a rail project where we couldn't drill and post fix a new beam into an existing column because the design life required was 120 years, and the permanent works designer could not get the guarantee on the resin fixings that would be required for the post fix. So we had to physically break out the column and install the rebar and then recast. So we'll take it through step by step here on these images. The front on the left hand side, you can see we've got an elevation there where our beam is going in, and then we've got this section cut through there. On the left, we've got the end product of what we want eventually, and that's a new beam that we've got shown in green attached to an existing column that's shown in grey. And on the right, we have what we started with, an existing reinforced concrete column. And the load path down this column is quite simple, and the load is spread evenly over the cross section of that column. So the load path is going top to bottom, and that load is distributed over the full cross-sectional area of that column. To enable the connection, we had to partially demolish the column section to expose the rebar. This meant that we only had part of the column left to take the existing axial load, like the load going through the column. There was only part of that column left, and all the load is now being transferred through that section. The next step was to insert the new rebar into the column void that we have just made, that I've shown in red. Now all the rebar is installed, we can recast the column and the new beam. However, where is the residual dead load, or the self-weight load stress acting? And also, where do these additional stresses get applied? So the residual dead load, or the loading from the structure above at the time before recasting, is applied to the grey section of the column. And this area is smaller than the previous because we'd broken some out. So the stresses in the column are now much higher. Any additional loading onto the column from above or from the new structure that is applied after casting is therefore applied evenly over the grey and the green section, because that's new loading, okay? The new loading gets distributed everywhere. The old loading is only going through the older section. So the grey part is already taking higher stresses. Therefore, this activity of putting additional load on could push the column past its capacity. So to sum up, once a structure is taking load, you can't remove that load without some form of jacking or preloading, and casting wet concrete into this section does not remove any loading, although the new concrete will take any additional loading afterwards. This is a really valuable lesson that applies to construction, jacking, propping, especially backpropping during RC floor construction. So one to really look out for. Okay, I'm now going to hand you over to James, who's going to take us through some more unconventional load paths, shall we say. So over to you, James.
Yeah, I'm going to be discussing some slightly less obvious load paths, things to watch out for, and showing a couple of examples of some interesting structures that we've come across over the last couple of years. The first one is a fairly straightforward scenario I'm just going to give you. We've got a simply supported beam or slab, reinforced concrete, cantilevering slab shown below. The primary reinforcement, or potentially the only reinforcement in the simply supported slab, is going to be the tension face, which is at the bottom. On a cantilevering slab, that would be on the tension face again, but that's the top face now. We've seen, I think there's an example in the cross reports from a few years ago that showed there was some cracks forming in a cantilevering slab, and the site team propped the end of the slab, and that's not a great idea. Essentially, you need to prop the whole slab if that's the case, because if you prop the end of a slab, it changes the load path and puts the bottom face into tension, and if there's no rebar there, you could be initiating the collapse yourself by propping it incorrectly. So just one little one to watch out for before I go into any examples. So yeah, this is an interesting structure that we have done the demolition sequence of. The structure's now been demolished. You can see at the front we've got these large columns with sort of balanced cantilevers on them, and on the sides of the structure also large cantilevering beams. So you'd have one compression leg with the closer one to the edge, and the rear leg here would be in tension to sort of balance the forces. This was quite a challenging job because of constraints on where the plant could access the structure to demolish it. So it required a very detailed sequence. And again, that was a demolition sequence. And that was because of site restrictions and also because of the odd structure that was built, or slightly unconventional structure that was built. A lot of the internal beams were also cantilevering on, but you can't really see that so much in this image, but they were not so obvious. So the soft strip and getting us down to site after the soft strip was pretty important to make sure that those were picked up and the demolition sequence is detailed to address those. A couple of interesting other cantilevering structures that we've come across recently. So on the left-hand side of the screen, there's an archive drawing that's a section view that shows, again, we've got the compression column at the bottom and the tension column here because we've got this massive load, very large beam column here that sticks out 3 meters beyond the edge, front edge of the structure. So the demolition sequencing for this structure would have to make sure that the cantilevers were trimmed or demolished prior to the structure on the right hand side, because if you took weight off that structure, the whole thing has the potential to tip over to the front. So something to bear in mind. The structure on the right hand side, I've done a little diagram to explain that because I don't think this image on the bottom right does it justice. It's a very weird structure. The top portion of the structure, you've got almost at the second floor, probably 270-degree views. So if you stand in the middle of this square that I've drawn at the top, there's no supporting columns or walls in the whole of this area. I think the best analogy I've got for how this works is if you had a bowl and you put it upside down over the corner of a table and pushed it to the point where it was clearly going to fall off, and you were holding it on the rear end with your hand to stop it from falling over. That's probably where we're at with this roof. Very interesting design, very cool, very awkward to demolish safely. But yeah, very interesting building. And yeah, and obviously you can see below there's also weird cantilevers going on beneath, but also need complex or a lot of thought to make sure that we're not going to initiate a premature collapse when we come to do the demolition of that structure. Another interesting example of building we came across recently is a structure with some hung floors. So this building's been built and the roof truss supports the second floor, so that the first floor level you've got a big open plan area on site. Now I don't, there's no historical information on this building, and I'm not sure the site team were aware that this was its construction when they started the soft strip. So it's a bit of an interesting one as to how to demolish that safely, because when you take off the first floor, so you would typically demolish top down. That's not gonna, if you did that in this instance, you would initiate a premature collapse, which, because of, in some instances, if you're in a green field, it might be okay to do that, but that's not the case here. We've got other structures around us. And another interesting item here is, as you take out the lower floors, you unrestrain the columns, the exterior columns that have got all of the weight going down them. So the weight of that floor and the floor that's up here goes up to the truss, across to the exterior columns, down the wall. But as you take out the lower floor, you unrestrain the column, so it doubles its effective length. So a lot to think about to make sure that those columns work, they're restrained, and also the demolition sequence is appropriate for that rather peculiar structure. Another one with hung slabs. This is a very weird building. I've been inside the structure in this area, the atrium area. And the first walk around the site, I didn't clock that there was hangers because they didn't look like hangers, they were hidden. You can see I've highlighted there's a hanger structure that's hung off this large trussed roof that hangs this slab that sticks out beyond the structure. So the top right image, you see out at ground level, I've looked up, and walking around the structure, I took this photo and thought, how does that work? Let's go back inside and investigate. And in the archive drawings, it does show a hanger that picks up the edge of this slab. Very odd construction, and again, would need thought as to how to demolish safely. I've done a little diagram to show how that works at the top. So that column there in the center is going to be in compression, and the column on the hanger is obviously pulling it down. So the columns on the left hand side are acting as a counterweight to prevent the whole thing tipping over. So you can't demolish working in from the left hand side. A couple of other interesting items that you may well come across is transfer beams within structures. You can see this on the left hand side, there's two large columns that come down that don't follow all the way down. So they come down to a large transfer beam that transfers to adjacent columns. One to watch out for in demolition sequencing. And on the right hand side, podium slabs. It's fairly common that you have a large podium slab at first or second floor level, and then the structure above there would be a different construction. Perhaps in this instance, on the right hand side, it's a masonry load-bearing structure with precast panels on the exterior walls, sat on the podium slab. Now the loads are applied on secondary beams and things on the podium slab so that it works, but that's not always the case, and it's always, as Josh mentioned earlier, critical to understand how the structure works and behaves prior to approaching the demolition. I'm going to go through an example of a space deck roof structure and the importance of understanding how that works and where the loads are, because these are very lightweight structures. They've been designed very well for their permanent case, and supporting them in the temporary case is not quite so straightforward. So an example here is this one is in Derby, the Eagle Centre. Coordinated did the work on the job to prop the structure, did a lift of a portion of that roof off that we justified, but I'm going to talk about the back propping to strengthen a portion of the structure. So typical examples of different supports for these types of roofs are shown at the bottom right. This roof had a few areas where the top chord was supported, a few areas where the bottom chord was supported with little trees similar to that frame capital, which it mentions on the bottom right. Not quite like that, but similar. So this was the intent that was provided by the Pernod Works engineers. Essentially, this blue line that's shown on the right-hand side is going to be a new support beam all the way along the structure. You can see the X's, that's one of the column trees, and you can see I've put an arrow to one of the column trees that's on that line that has to temporarily come out, or the support from that column has got to be taken out in order to put the new beam in. The image on the screen was from the Pernod Works engineers, which looks like a fairly straightforward propping solution that we'd have to come up with, provide a supporting tower here, as shown there. Not quite so straightforward, it turns out. So these are the archive drawings of that structure, which obviously is quite, this is just for the diagonal members within the space deck roof. And you can see it's labeled up on the right hand side. You can see the letters. So there's element J, element H, element L, element K. They're all different elements, and I've listed out the different capacities of those elements because they're pretty drastically different depending on their location in relation to the supporting columns. So we've got some that have as little capacity as 6 kilonewtons, and some as high as around 30 kilonewtons. So we've done a full model analysis, which I've overlaid in the background of the image on the right to determine which elements were going to be highly stressed, or the stress in each element in the supporting case with our props there. And initially we did we looked at this propping scenario, and unfortunately the members that or the diagonal members that were directly above these props attracted a lot of load, and they were not designed to attract a lot of load in their permanent case. And essentially that was never going to work. So we ended up supporting the top chord of the truss instead. And this is our design, and we had to support it in more locations than we initially expected, because of how weak all of those elements were, or well designed, you could say, for the permanent case, efficiently designed, but not very robust. So yeah, a seemingly reasonable approach. It didn't work because of how susceptible these structures are to any change in load support condition. So this is a very good example that shows how critical it is to obtain that information, this as-built information. And if we were dealing with a similar structure that we didn't have the as-built information, it would have been very difficult to have justified how to prop that roof. So yeah, information is key. And just to emphasize that, a lot of these members visually were the same diameter as one another. It was just the different thickness of the elements. So visually, you wouldn't have been able to tell unless you drilled into these elements or you put a depth gauge on them. So yeah, importance of getting the correct information at the start has been thoroughly highlighted, I think, there. I'm going to go through another complex load path. So this is a tower crane grillage example. When we are given these to design, there is the vertical force that's coming down the tower crane. There's the horizontal force that is applied left to right in any direction. The moment, again, is the moment of the overturning moment of the crane, which could be applied at any orientation. And then we've also got a torque from the when the crane is actually rotating. To show that visually, vertical forces are applied something like this. The moments applied something like this. This is obviously very much on a 90-degree angle. We've got to consider, if it's a symmetrical base, we might be considering 0 and 45-degree scenarios. For a grillage, though, typically we consider every 5-degree increment to make sure that we're modeling the worst case scenario for the grillage, which is obviously a hell of a lot of load cases. We've also got the horizontal forces and the torque forces. And this is an example of an output from a tower crane grillage. And it's always important when we look at these to interrogate the model. Does the load transfer through the model as expected? You can see on the top right, we've got the axial compression and tension that's going mostly into the bracing members. And on the top left, we've got the bending moments being transferred through the main beams of the structure in the stronger axis, and on the bottom left, moments in the weak axis. But it's very important to understand and follow the load paths and also the moments, and to make sure that what we expect to happen is happening, to make sure the model's working correctly and deflecting correctly. I'm going to bring up briefly wind loading or instability of structures. So if we're applying a lateral load to the structure, so wind or notional, typically we're applying wind loads to a cladding panels or walls, that will be transferred to the floors of a structure, and then through diaphragm action it will be transferred back to the stability mechanism for the structure, which for a masonry structure we're typically talking masonry shear walls. For concrete structures, typically reinforced concrete cores or reinforced concrete shear walls, potentially acting as a moment frame. And then steel structures, again, typically reinforced concrete cores or steel braced portions of the structure, or again, a moment frame. So when a lateral load path is interrupted, for example, you're keeping a facade up and the structure that provided that lateral restraint to it was removed, we are going to have to design some temporary works to make sure that in the interim, the load paths are maintained and there is support to the structure. Just typical examples of a facade retention and propping to some large shear walls at the top of the structure there. Going to give one more example, in fact two. This one applies quite well to typical overall global stability of a structure during demolition. So you imagine I've sort of drawn the building back in. The Google Maps image is kind of half demolished it, which shows they did exactly what we intended in the demolition. Drawing it back in with the orange lines on the right. So we've got quite a long, thin structure there. On the right-hand side of that, we've got a neighboring structure. It's not in contact with, but it's very close to our structure. Due to that, we had to take down one side of the structure first, but a top-down methodology with a Brock, because we didn't want the high reach working so close to the neighboring building. That caused issues because this building relied on the two cores, one at the south, one at the north, for stability, and acted like a big beam laterally, the floor slabs did, to resist wind loading. So when we took one of those cores down, wind loading that was going to hit the side of that structure was going to put a torsional force on the remaining south core, which we checked and found it would overstress the core basically. So we introduced some stability bracing halfway through the structure, which is highlighted by the blue lines on the image on the top left. And in the middle of the screen, you can see what that looked like in section to provide temporary stability to that structure for the wind loads and notional loads during the initial portion of the demolition works. And then following that, we also checked the structure so that when they did the demolition works and got past the point where our bracing was, that it still worked, which is basically the image on the right hand side, which Google Maps have conveniently grabbed for us. One more load path I was going to go through, which is a slightly less obvious, well, not obvious, it's fairly obvious, but less thought about, shall we say. So we typically design quite a few tower crane tie or cast-in ties for cores a couple of years, I'd guess. And this is a interesting example of, I believe it's Leadenhall, one Leadenhall, which is now pretty much finished, or the main construction is finished. So there's two different tie types, and they've gone into into the concrete core of the structure, but they've been aligned to go as close to the return walls as possible, so that we can utilize the shear wall behind to prevent the whole thing, or to resist the large lateral forces that have been applied. You can see how we've applied that force, and then because the double connection is quite a large connection, we've had to actually introduce a large gusset on the inside to transfer the forces back to the shear wall effectively, including some shear studs and things like that. We've also included additional reinforcement in the slab to make sure that to complete the load path into the structure, so there's not a local failure, a local pullout. And once the load is in the structure, that's when it becomes the problem of the permanent works engineer, shall we say. But we need to make sure that our ties are sufficiently designed and detailed so they don't pull out. I believe that is my last slide. So I'm going to hand over to Richard now, who's going to take us through another example.
Yeah, one more example for the Gramophone Works. So the Gramophone Works is a building in London that we did a few years ago. From the plan view of the building, you can see lots of these big columns about. As part of the main scheme, it was a cut and carve job. So you see these big blocked off areas. They were the areas for new cores to go in. And so there was going to be a lot of cutting up of the slab of this building, taking out part of the columns in areas. And the building initially had two large towers, one at the top left, one at the bottom right. Originally, you might think that they might be providing some stability to the structure, but alas, no. They were completely separate and self-standing. So it was the columns themselves that were giving support laterally to the building as well. And the walls around the perimeter, we discovered quite quickly, weren't structurally needed either. So just after the soft strip, we were able to remove those walls and get a proper idea of what the building was doing. And you can see these very large columns with the big mushroom heads at the top, and they're actually in the basement as well at the bottom. And it's because it was an old gramophone works, you needed these large columns to take out the surrounding vibrations so that you had some nice steady floors to make the gramophones when they were doing such things at the time. So when you have all these columns holding up these floors, you get a very organized and neat and tidy load path going through the structure. Keen-eyed people will notice I've left out the one in the middle by accident, but that was a slab at the time, and the hole was put in afterwards. But so this load path is very organized, very typical. But to make these large holes, you'll see that you interrupt a lot of these lines. So on the left, you're interrupting lines going towards the columns at the bottom, and some bits of slab are left floating in certain locations, which all this had to be considered. So what we did to consider all these load paths was we looked at where these red lines that I've drawn on this picture are interrupted. So where they're interrupted, you're interrupting the load path, and you need to consider how you're going to support the slab when its load path have been changed. In some locations, the load path will be diverted through and around the slab that's remaining. So in the top on the second one, you can see that there's a riser just coming out of the middle core there. That will cause an interrupt from the middle, but from the top, the load will just reorientate round that hole. So that wouldn't have been a problem for that location. But these large holes needed some thought about how we were going to support this load path. When we went and looked at it properly, you can see these large holes, and this was done in one axis and the other axis to help us decide where props were needed and where the loads would reorientate themselves. And this is where we ended up putting the props. So in the middle, just next to that core there, you can see that that really did need a prop in there, and that was obvious from just having a look at where the load paths went. You were interrupting how that slab was supported. Same with the line of props on the other side of that. Because you were cutting out a chunk of the floor, you had to support that slab directly because it wasn't supported by the column anymore. And in the load path, you could see there was heading straight towards that column it was now disconnected from. In the bottom right, it was more obvious you had a bit of slab that was hanging by itself, and obviously that wasn't supported by anything, so you needed a prop tower in there to support it. But when you install all these and you reanalyze the load path, you can see that the loads start to go towards the props rather than towards the columns that they originally did. So the props themselves had to be quite robust rather than just a simple line of props. You can see I've got a lovely line of prop towers in the middle there. Just prop detail D there to make sure that the slab itself was supported enough in lateral movement and in self-weight while the construction activities were going on in that core right next to it. Now, the towers that were self-standing also had a bit of work to be done to it. You can see them in the top left, bottom right there. They had some interesting load paths as well. So that's the typical existing load path for the prop towers. You can see them coming down. Initially, nice, clear. They weren't connected to the structure, so there was no additional lateral loading from the structure considered. And what we wanted to do was pin the entire thing so that we could extend the lift shaft down. So at the bottom, you can see, compared to the previous one, there's going to be a big gap at the very bottom of this load path. As Josh said earlier, the load tends to want to go back into the ground, and we've just disconnected the entire thing. So we needed a design to redivert these load paths through all these propping arrangements. In the higher levels, we had some extra openings to make, and they were just propped to make sure that the load path wasn't interrupted them. Just some simple propping going down to carry the self-weight of the structure. And then when you get to the bottom, you can see these blue beams coming out of the tower to redivert the load. So the load comes down, comes through those blue beams, and then down into some temporary piles that we had in the ground there. So the temporary piles successfully rediverted the load, and you can see that the load path continues on down the structure through that blue pile, through that blue beam, and down into piles and back into the ground where it originally was, back to where it was happy. And from that, I think I will pass back to Josh if he wants to talk through today's topic.
Thank you. Thanks, Richie. A kind of a deep dive into that project. Very interesting project. Thank you. So just to round up today's discussion and today's topic and load paths. So it's really important, as I think we've hammered home the point a number of times, to understand the structure. And with that understanding of the structure, we can understand what the sequence is, understand what the problem is, and then get to the right solution. That's part of the GIGO, garbage in, garbage out. We need to have the right information coming in, or gathering the right information at the beginning to get the right output at the end of the project. And that's pretty much all we have time for today. There's lots and lots of content out there. I've just kind of slapped on little bits and bobs that we've got on there. So there's a BRE, there's lots of building guides on there about cut and carving. There's Temporary Works Forum, which has got a lot of great content on there online, which is freely available. In terms of temporary works, there's a couple of good guides that I've listed on there. So there's temporary works in principles, the yellow one on the left. There's a new one, which is part 2, which I've put in there as well, published by the ICE. There's 6187, BS 6187 about demolition, partial and full demolition, which I mentioned earlier, as well as BS 5975, which is the temporary works British standard. But there's lots of really good information out there for you to see.